And welcome everyone once again to this GENI webinar. And my name is Ben Newton. I am a graduate student at the University of North Carolina at Chapel Hill. And we are honored to be able to host and organize these GENI webinars. We've got one set up for each month for the rest of the year. And so we hope you look forward to the remaining in the series of webinars. And I just want to recognize Vic Thomas, who is joining us as well. He works for the GPO, the GENI Project Office. Thanks, Vic, for coming and joining us for this webinar. And we are excited today to have a webinar on PhantomNet, and it's my pleasure to introduce Kobus van der Merwe, who is a professor in the School of Computing at the University of Utah and a co-director of the Flux Research Group. He worked for 14 years at AT&T research labs in New Jersey before coming to the University of Utah. And so without further ado, we would like to welcome Kobus and thank him again for his willingness to present to us today.
All right, great. Thanks, Ben. So I think I'm sharing my PDF viewer. Can you guys see the slides?
Looks perfect. It looks great.
Okay. So this seems to be playing by itself. Hang on one second. Don't have that. So I think Ben basically said all of this already, except maybe that it's a South African accent if you haven't placed it yet. So brief motivation. There's a lot of mobile networking research that gets done. Much of that is pretty theoretical, often sometimes very abstract and conceptual. And there's mainly two reasons for that. One is that it's pretty complicated, right? So if you talk about 4G, then you have this alphabet soup, and now we're moving to 5G, and it's a different alphabet soup. And then 5G is also introducing a whole bunch of its own set of soft technologies, and they are by themselves pretty complicated. And then the second reason is that really there's been a lack of realistic experimental platforms on which to do more practical work. So we built PhantomNet to try to address that concern, and we'd like to introduce you today to PhantomNet. So PhantomNet is a testbed to enable research in mobile networking. So what we're going to try to do today is to demonstrate the PhantomNet capabilities live. So we're going to instantiate a very small open source 4G mobile network using the open interface software. The slides are available on the URL that was sent out with the webinar information. The slides are pretty much self-contained, so you should be able to follow along and do it on your own. I'm pretty much planning to just move ahead, so I'm not going to necessarily wait for everyone to catch up, but you should be able to do that on your own. And both Ben and I will be available afterwards to help you to that stuff. So the experiments take a little while to swap in on PhantomNet, and we'll talk a little bit about why that is the case. So while that's happening, we will talk a little bit about what PhantomNet is, and then also a little bit of mobile networking background and concepts, just so that you understand what we're trying to do here. And then we'll finish up with just the status of PhantomNet, other things that are available in PhantomNet, and I hope to do just a quick other demo of some of the real that we got working recently. So our goals is really just to help you understand what PhantomNet is and how you can use it for your research and teaching. Right. So on to the next deck. Would be the second one on the web page. So basically, you're gonna log in to PhantomNet using your GENI credentials. We also have a PhantomNet specific login where you can log in as a PhantomNet user without being a GENI user. We're going to swap in this profile, and I'm going to talk a little bit about what a profile means later on, based on the open air interface software. Then we're going to talk about PhantomNet and what the 4G architecture, and play with the instance, and then swap out again. So at this point, I'm going to switch to the live demo. I will probably be going back and forth between the slides and the demo. But like I said before, you should be able to follow along if you use the slides that are available from the website. Okay, so can you all see my my Chrome browser at this point?
Yep, we can see it.
All right. So I'm going to use the GENI user login. And you'll get this big GENI thing, which is really a button. You'll click on that. You will search for your institution. So this part will obviously be institution specific. So normally I would have gotten a actual authentication page at this point where I would have logged in with my institutional credentials. I did this ahead of time, and so we're going to skip that step. I click on authorized, and now I'm authenticated with PhantomNet, and I'm actually entering the PhantomNet portal. And it seems to be taking its sweet time loading.
Let me just say one thing. Again, this is Ben Newton from the University of North Carolina. If people have specific issues or questions as they go through this, one of which may be the need to have a GENI project associated with your account. If you have issues like that, just go ahead and type in the chat window, and I'll try to respond to those questions and chats. Thank you.
Thanks, Ben. All right, so this is the landing page on the PhantomNet portal. If any of you did the Cloud Lab webinar last month, it's essentially the same environment. This one is specific to the PhantomNet environment. The Cloud Lab one was specific to the cloud infrastructure. So first thing we're going to do is we have a default profile selected here, which is one VM. This is just sort of a default that we pick for everyone. That's not what we're interested in today. So we're going to change the profile. And as you can see here, we can see all the different profiles that are available, that's visible to me. And we're going to pick the open air interface simulation one, open OAI underscore sim underscore S. Gives a very brief description of what this profile is about. We're going to select that profile. We're back to the selected profile page. We click on next. So typically there could be a second step where if the profile has parameters associated with it, like the number of nodes or things like that, we might have we might have parameterized the profile. In this case, for this simple profile, there's no parameters, so we just skip to the final step straight away. So we can give our experiment a name. So let's say open air interface, okay, underscore Kobus webinar. And this is optional. You don't have to give it a name. If you don't give it a name, the system will just assign it a name by itself. And then we click the finish button, and the infrastructure will now go off and instantiate that profile for me. So let's talk a little bit about what a profile means at this point. In the simplest instance, you can simply think of a profile as a canned experiment, right? This is something that someone else has set up, and it was saved as with all its dependencies in this profile format, and the profile specifies both the resources that are required in terms of the hardware, the software that's needed, the images that need to be loaded, basically everything to make that experiment be repeatable. So there's two ways then that we can think of a profile. The first one is, as I just suggested, is sort of to allow repeatability, right? If you've done some experiment, maybe you've written a paper, and you now want to make that experiment available to other users so that they can verify your results or maybe extend on it. So that is how we can think of a profile. It allows us to do this repeatable experimentation. In the context of the actual experimental process, we can think of a profile as sort of a starting point, right? So I can start with a profile, and then maybe I pick a profile that's close to the kind of research that I want to do, and then I might modify that and do my experiment, and then create my own profile. Right? So it becomes part of your experimental process to create these profiles. All right. So in the meantime, you might have noticed that these two nodes appeared in the portal window. So the state of our experiment is indicated here as booting. So we have now been allocated the two physical nodes that will be part of this experiment. And this process, once it's allocated till it should be ready, it's probably going to take 12 to 13 minutes. But at this point, we can see here, if I hover over that node, you can see that this node has been allocated TC498. It shows the node status here, saying the status is changing, it's reloading. So, and the same for node 1, node 0. So just to give you a little bit of a sense of what's happening behind the scenes, right? So we have this profile, or this recipe, or canned experiment, whichever way you want to think about it. And the PhantomNet infrastructure, or really the EmuLab infrastructure behind PhantomNet, is now taking that recipe, and it found two nodes which satisfies the requirement for that. It's allocated those nodes, and now it's going through the process to essentially clean and re-image these PCs to instantiate the software that was captured in the profile. Right? And so if you were to look at the state here, you would see it rebooting and reloading, and going through lots of different reboot processes in the whole process of getting the experiment up. All right, so we're going to leave the experiment or the portal at this point and go back to our presentation. So just went through all of this. This was the institutional login page that I didn't see because I logged in before. I think we saw all the rest of it. So what did we just do, right? And I kind of described that in passing, but we instantiated an open air interface 4G mobile network profile in the PhantomNet testbed. And in the next couple of slides, I want to kind of tease apart the sentence and say, well, what does this all mean? So before we talk about what open air interface is and what PhantomNet is, I need to give a little bit of background on 4G just so that we're on the same page. Now, I'm assuming you, at least at some level, all know what 4G is. 4G came after 3G, and 3G came after 2G, and these are generations of the mobile network. So this is kind of a nice architectural diagram from this book, SAE and the Evolved Packet Core. They kind of show a couple of important things. So the first thing to notice, when we talk about 4G, we really talk about LTE as long-term evolution, which is the radio access technology. And then we talk about what is normally called an evolved packet core, as suggested in the book title. And what that is saying is that in 4G, the core mobile network is a purely packet-based network, right? So before, with 3G, we did have a packet-based network. We did have a packet core, but that was only for data, right? If you use your 3G phone and went to the internet, then you did go through an all-packet network. However, in the 3G network, if you did voice, other than Skype, right? So Skype would have gone over the data network as well. But if you did regular voice service as provided by your mobile network provider, you would actually go off to a separate circuit switch network. That's no longer the case in 4G, right? So everything is packet-based. And so there's this INS domain or INS cloud, which essentially is doing the voice services over the packet core in the 4G world. All right, so here is a little bit slightly more detailed diagram of the whole evolved packet core architecture. This is, as you can tell, very involved. It also covers all the previous generations. But just to sort of tease our way through this, here we have at the bottom, we have LTE. The base stations in LTE are called eNode Bs. So those, think of those as the cell towers that you might see on the side of the road. So from an eNode B, if you were to go to the internet, your path would lead, the data plane path would lead through something that's called an S gateway or a serving gateway. And then from there, it goes to a P gateway or a PBN gateway. And from there, you would pop out onto the actual internet. So as I suggested, this is the data path. This is how your packets would flow from your phone connected to LTE and then all the way through to the internet. There's also a couple of important control plane components in LTE. The most important one is the MME, the mobility management element, and the HSS, the home subscriber service. So the MME and the HSS deals with authentication. So if your phone is switched on the first time, you essentially authenticate with the MME. The MME turns around and consults with the HSS to make sure you're a paid up subscriber and you can come onto the network. And when that is deemed to be so, the MME is the thing that talks to the P gateway, the S gateway, and the eNode B to set up a tunnel for your traffic from the eNode B all the way through the network. Right? And sort of implied with what I just said, there's a lot of state associated with mobile networks. Every device, every UE gets a tunnel or a set of tunnels really that stretches from the eNode B to the S gateway, and then a separate tunnel from the S gateway to the P gateway. And all of this state is being maintained by the network while your phone is active. Right? This is slightly so sort of just pulled out the basic components that we from that bigger picture. Really, the essential pieces to do connectivity in a 4G network. A little bit more detail, if we add to that, there's this thing called the PCRF, policy and charging rule function. There are these offline and online charging services. These are supplementary things to the basic core functionality. The PCRF is the thing that the IMS cloud that we talked about before that will be doing your voice communication in a 4G network. It would actually communicate with the PCRF, which would communicate with the P gateway to set up dedicated bearers for your voice call to make sure that they have the priority needed for carrier-grade voice communication. So if we dig down the protocol stack a little bit, so if you're running an application on your phone, then of course there's the application layer, right? It might be your browser communicating with a web server in the internet. If you look one level down at the IP connectivity, then there's this tunnel that basically connects your UE or your mobile device to the P gateway. And so from an IP perspective, the P gateway is your first IP hop, the first IP hop that is visible to your application layer. And then from there, it would pop out onto the internet. Now, because the EPC or the 4G core mobile network is an all packet-based network, all of these components by themselves live on top of an IP substrate, right? So the serving gateway and the P gateway are really just elements on top of a regular IP network. So they communicate with each other, and so does the eNode B, which is not shown in this figure. They communicate with each other over what you can think of as essentially an IP transport network. But that IP network, the IP transport network, is not visible to you as a UE, right? All that you see is this tunnel that takes you to the P gateway. In a little bit more detail, so you have these filters that you can set up. I mentioned briefly before that if you're doing voice calls, for example, you get a dedicated bearer or a tunnel set up for that. So we have these filters both on the P gateway and on the actual device, on your handset, that would siphon off the right set of traffic to make use of those dedicated bearers, right? So that's the way in which voice calls, for example, can receive preferential treatment in terms of traffic being carried through the packet network. If we look a little bit deeper into one of these tunnels, so the tunnel goes between the eNode B and the S gateway, and then another tunnel between the S gateway and the P gateway. If we look at the packet that on the network in between these two devices, we have the regular IP header, which would basically say, oh, I know as a S gateway, I know I need to send traffic to this P gateway. pure, simple IP, normal IP. Inside of that, we have the tunnel header. So the GTP tunnel, that rides on top of UDP. And then inside of that, we have our actual, the user payload associated with the traffic from the mobile device. This busy slide is basically just showing the normal attach procedure. I'm not going to go through the details here, but again, your UE communicates with the ENO-B, which communicates with the MME. The MME would communicate with the HSS to verify that you're allowed on the network, would communicate with the UE to verify that it's really you. Once you've gone through all of that, the MME communicates with the S gateway and the P gateway to set up the bearers in the core network. Once that is set up, there's also a bearer being set up across the radio access network to go from your device to the base station. And when you detach, there's a similar procedure to do the detach. Okay, so that's your really very quick introduction to mobile networking and specifically 4G. So what is PhantomNet then? Well, we already said it's a mobile testbed and aim to enable research at this intersection of mobile networking, cloud computing, and software-defined networking. It has this mix of hardware and software, and it's remotely accessible and shareable. Right? The way I'm accessing it today via this portal, that's the way you can access it via the portal. Right? We don't have any special privileges that just because it's locally located in Utah. And it enables a whole bunch of research, right? So we've done work in NAV and SDN, some core networking. You can also do radio access network work or on the endpoint themselves. So in pictorial form, here's how you can think of it. Basically a Lego set, right? I have here the hardware components. We have off-the-shelf UEs, basically Android smartphones. We have off-the-shelf small cells, B devices. We have software-defined radios. And then all of the radio gear is interconnected by this programmable attenuator. And what that gives us is that we basically operate in a very controlled radio access network, right? So we can control the attenuation between all these devices. We can do very repeatable experimentation. And then this is evolved from a more traditional network testbed. So we have, of course, compute nodes and switches. Then we have different software components. So one of the big ones we have access to is OpenEPC. That is a fairly mature but not production quality EPC stack. So it implements all of the core mobile network components. OpenLTE and Open Air Interface are two open source mobile networking stacks. The webinar today, we're going to focus on Open Air Interface. So these two open source stacks are not quite as mature as OpenEPC, but there's a lot of development that's happening within those. And so they actually becoming more mature all the time. And then on the side here we have the MLab control, right? And so again, basically the way you want to think of it is I have all these Lego pieces and I can put them together in any which way that makes sense for my experimentation, and then it will get instantiated for me on the infrastructure. So in slightly more pictorial form here, we have different users. They input their request to MLab and different experiments get instantiated, right? And so this is the typical PhantomNet workflow. So what can you do with it? Well, the OpenEPC software stack allows us to do an emulated RAN and then a somewhat realistic core network. This is kind of nice if you want to do more scalable experiments where you have a lot of UEs. Of course, the RAN here is not realistic. It's just a regular Ethernet, and so it's depending on what you want to do, this may or may not fit what you want to do. It's a great thing for teaching. because you can have a lot of these instances being instantiated at the same time. If we use the real radio equipment, then you can access an Android device. You can run whatever applications you want to run on there. So one thing I should say up front is when you get access to these resources, they're basically yours for the duration of the experiment, right? So you get access to an Android device, you can install your own applications on that, you can do with it whatever you like. And similarly for the other nodes. The only thing that you can't do that with is the commercial off-the-shelf Ds. Essentially, they're not programmable. They're configurable, but they're not. You can't run your own software on there. And then, of course, this only works if once you're done and you give back your resources, we can scrub it clean and give it to another user. So if you're interested in something more esoteric, your own core network, your own protocols across the RAN, we have these software-defined radio instances, both on the UE side and on the ENOD side. And you can use some of these open source stacks that we already mentioned to bootstrap you in doing that. So these are just a bunch of pictures of the actual hardware. These are the servers that this run on. These are the Android device that we use. This is the off-the-shelf Enode B in its Faraday box, the SDR equipment in its Faraday box. This is the system all put together. We have these Faraday cages for the SDR, the off-the-shelf Enode Bs, and the phones. This black box here, that's our attenuator that connects everything together. Brief word on the software. Well, I think I'm going to skip that in the interest of time, but OpenEPC, we have OpenEPC release 5. It's not open source, but we have a binary license that allow our users to use it. OpenLTE and Open Air Interface, real open source, not quite as mature, but becoming more mature as we go on. So for today's webinar, the profile that we swapped in is one of the open source profiles, specifically Open Air Interface. And then hopefully at the end, I'll show you another profile that makes use of the real radio hardware. Okay, where we left off with PhantomNet, we instantiated this profile. So in pictorial form, it's going to look something like this, right? So we have two physical nodes. We have node 0 and node 1, and we're going to run software that open air interface software that does an emulated UE and eNode B. And then on the other node, we're going to run an MME, an S and P gateway combined, and a HSA, right? So you can map this onto the 4G architecture pictures that we had earlier in the slide. So open air interface, again, I'm going to skip this, but this is real open source software. Let's say one thing here that's really exciting is that you can run the software both in simulated mode and on real hardware, right? So the way we're running it today, as I was showing here, this interface between node 0 and node 1 is just a regular Ethernet interface. And so we're not, and in fact, the UE and the eNode B, which should in real world would have a radio network between them, is combined in one emulated node. But it's the same set of software, and you can run the same set of software but configured slightly differently on a software-defined radio, in which case your eNode B would be running on real hardware, SDR hardware, and your UE can be an off-the-shelf UE like an Android device. So it's very flexible and again, very exciting that there's open source of this caliber available. Okay, let me switch at this point back to the experiment. So this is our experiment window. As you can see here, our experiment is now ready. It's fully swapped in. We see these nodes are all green. The status of the experiment itself is green. So we're gonna, at this point, these nodes just sit there, nothing really running on them. And so we're gonna go through the exercise of starting up the open air interface software on them to allow us to do our experiment. So we need a little bit of workspace, as it were. So the first thing we're going to do is just, and this is all just scaffolding, if you like, setting up an environment for us to do our experiment in. So what we're going to do is we can access these nodes via SSH. If I click on this, would open a browser, a terminal window to that device. But that's not how we're going to access it today. We're going to access it with a in-browser shell. Right? So if I click on this, I click the shell button, then it opens up a shell directly on that node via the browser. Right? And I can do the same with the other one. And this is actually kind of neat because it allows us to interact with our experiment with only using a browser. So we're going to start up VNC on these so that we can run an X terminal in them. Okay, so once that's done, we get this clickable link. We do not have a valid certificate, so if you were to do this, you'll get this warning saying the certificate is not valid, so do whatever your browser requires you to do to go through with that. Enter the password that you provided for the VNC session, and now we get these 4 X windows running on our node 0, right? And we can do the same thing with node 1. Okay, so now we're all set up for a work environment. So now we're going to start up the actual software, the open air interface software. So now recall that our node 0 is running the UE and the eNode B combined, and node 1 is running the MME and S gateway and HSS. So we're first going to set up the node 1 to run the core network. And the way we do that, we have a nifty little script that will do everything for us. So we run the core components and the HSS. So these warnings is just because it's trying to clean up if there was any previous sessions going on. So we can attach to the console of these. So you should see something along those lines when you do that. Okay, and so this is showing that that the table that was just flashing by is showing that there's no current UEs connected. Okay, so now our core network is ready, but we want to be able to see what's going on. And so we're going to start Wireshark on one of our core network nodes. So we're going to first figure out what interface to use, because these nodes, the physical nodes, actually have a bunch of interfaces, and you might get assigned to different interfaces when the experiment sets up. So we can see here that the interface that we're looking for is on physical interface E3. So that's what we'll use when we start a Wireshark. So we're going to do sudo Wireshark, and we should get a bunch of warnings. Just click through those. We're going to select E3 as the interface of interest, and we start Wireshark. So these protocols are pretty chatty, so we're going to limit the protocols of interest to the S1AP protocol. And Wireshark is pretty neat in that it understands all these protocols, and as you'll see in a minute, allows us to go look at those protocols in excruciating detail. All right, so now we're all set up with our core network. So we're going to swap over to the node that is doing our emulated UE and inode B, and we're going to start that up. Okay, lots of stuff scrolling by. So hopefully it all worked out. So if we go back to the core network node, we can see we have a bearer now. We have one UE that's attached. If we look at what Wireshark captured, it captured this whole authentication between the inode B and the MME, right? So, and you can click on into any of these and get all the details associated with that. What's contents of the messages. Okay. So now we have a UE or an emulated UE attached. So let's see if we can see this thing actually working. So as part of the setting up this emulated UE, a new interface, a virtual interface, gets created on the physical node. And so this one here, OIP1, is the one that we'll be using, and that is associated with the tunnel from the UE to the inode B and up to the internet. So we're going to do a ping. We're going to select that interface, and let's say we ping Google. Okay. So packet went through. If you were paying attention, you might have seen something scroll by over here. If we go back to our Wireshark session, if we remove that, we should see one ping request and reply that went through. Okay, so we basically have a somewhat primitive but fully functional 4G mobile network. Right? From our UE, we went through this inode B, emulated inode B through the S and P gateway out to the internet. So it is actually functional. So just to show that we can do more than ping, we're going to try to do a wget. So we're going to just use this. So in order to do the wget, we need to mess with the nodes routing tables a little bit on the UE side. So we're going to add a route that will take us to the subnet associated with Google. So we'll just say 216.58.219 .0/24 1. So we should now be able to route to that in our table. That's going to take us out on this virtual interface, and we can just do a wget full.com, and we get that down, right? So that's pretty much the essence of this very simple profile. So once we're done with our experiment, so let me actually pause at this point, and I don't know how many people stayed with us through this, but any questions at this point in time? I'm going to take that as a no.
I have one question, Kobus. So the only thing that is special about what we're doing with PhantomNet for this specific demonstration is just the emulated software that does the eNode B and the HSS and such. Otherwise, these are just two regular nodes that you could use for other GENI experiments. Is that correct?
That's totally correct.
Great, but yes, obviously, PhantomNet encompasses other hardware for other research studies and whatnot.
Exactly, right. And so what I'm going to show in a minute is how we can use some of those other hardware that's more real radio gear, as it were.
Great, thank you.
I think the interesting thing, just to map your question onto what makes open air interface really interesting is that you can essentially use the same software stack and run it in the way that we're doing it here, right? Emulated 4G mobile network. You take the same software, run it on software-defined radio, and now I have real radio gear that can communicate with off-the-shelf eNode B, off-the-shelf UE, right? Or if you're so inclined, you can run the same software or version of the software on software-defined radio on the UE side, and now I have a complete open source stack from the UE all the way through to the core network, right? And it's the same software, so again, you can go from an emulated environment to a real radio environment with essentially the same software.
Great, thank you so much.
No other questions? I'm going to go back to the portal. I'm going to terminate this experiment. So again, what this basically is doing is taking those nodes that were allocated to us, it's putting them back into the pool, and other people can use it. So before we go to the other experiment, let me just see if there was anything else I wanted to cover here. No, I think that's it. So let me switch to the third presentation. Okay, so what have we done? Well, we instantiated this open air interface in a simulated RAN, and then with a very basic EPC. So other things that PhantomNet has at the moment, we have lots of resources, right? So when any of my students do any work, we typically create a profile out of that. We write a little tutorial, we put it on our wiki. So all of these profiles are available for users to serve as sort of a starting point for their own research, right? So some of the things that we've done SDN related work, extending 4G with cloud and SDN, which really take us more into a 5G sort of environment. We've done NFV orchestration work using, again, standard EPC. We have done work more recently on Internet of Things and basically using an open air interface environment to radically change the way that you do the architecture over the RAN and in the core network. I've also used PhantomNet for teaching. Those resources, the material for that are available if anyone is interested in using this for teaching. It's a great teaching tool, right? Because you can actually, like we just saw in this example, you can run Wireshark, you see the actual messages being exchanged. So it's a great way for sort of hands-on learning of mobile networking. Right, so in terms of real hardware, we have 28 Nexus 5 phones. In our hardware setup, we have 8 off-the-shelf Bs. These are IP access small cells. We have 12 SDR kits, if you will, where we have combining a USRP B2010 with an Intel NUC, and the combination gets allocated as an SDR node. And then we have this 32 by 16 programmable attenuator that connects all the radio gear. And then we have working profiles for UE and InnoD and EPC core. We have other profiles on the way. The key thing here in terms of accessing it, you access it in exactly the same way, right? Just like what I showed you now for this profile, you would select the right profile, would get swapped in, but in that case, you would interact with real hardware. So the demo setup, this is basically what the demo setup looks like. So in terms of hardware, we have a UE.
Kobus, I'm not seeing your slides for some reason. I assume I'm not the only one. I see a blue screen. I see your mouse.
I am sharing. Let me stop sharing.
Is it sharing?
Again. How about now?
No.
It still shows as blank for me.
Yep, just a blue screen. I could see your mouse moving around previously. I can see your mouse now.
Okay, well let me try to share the entire screen. If that works.
It was certainly working before.
How about now?
No, just a blue screen.
No.
Unless
Blue Jeans
So
is playing.
I'm gonna share in the chat window the URL that people can go to, and you can click on the status slide deck.
Well, I'm just about to move off of that actually. So let me see if I go to the browser, whether that works. Is that visible?
Yeah, that's visible.
All right. Well, then let's just skip the slides. In fact, I could probably show the slides here. Can you see these slides?
Yes, we can see those.
All right. So basically, just wanted to show this figure. So what we're going to have in the demo is a UE, so Android phone in one of these isolation boxes, going through the big box attenuator to an off-the-shelf InnoD, and then we're using OpenEPC in the core. And then we, much like what we had access to the core components in what we just did, we can have access to the core components through the portal. But then we also will have Adb access to the UE via a ADB host, and there's a ADB proxy that sits in between. Right? So this is sort of the picture you should have in your mind as we go to the physical setup, or the setup for the physical demo. I'm going to log out of this. So the profile I'm using for that is not accessible to GENI users at this point. And so I have to log in through my native PhantomNet account to access it. Okay, so I can go through the whole swapping thing again, but I swapped one in ahead of time. And so actually I have two of them swapped in. I just click on that. And this is the picture of our topology. So this is the real UE, so that's the phone. This is the real InnoDB. So this link here is going through that attenuator box. And we have an S gateway, we have a P gateway, and we have an EPC node that runs a variety of sort of support core mobile network functions. Right? So this is essentially the same setup that we showed with the previous experiment, but now using real hardware, using a different software stack. So this is OpenEPC, whereas the previous one was from Open Air Interface. This node here, ADB target, is just an auxiliary node that we swap in just to make it easier. You can actually select your own machine to be an ADB target, but by doing it like this, we can install all the tools that we need on this machine readily, and so it makes it easier for users. Okay, so the first thing I'm going to do is I'm going to open a shell to the S gateway just so we can sort of see what's going on. And I'm going to do a similar thing to what we did before. I'm going to attach to the MME. Right? And so this is sort of the console of the MME that will show us what's going on. All right, so now I'm going to access this ADB target. And actually, at this point, I will want to share my whole screen. So let me see if that is possible. Can you see the whole screen? Oh, the wrong one.
Yes, I see it.
Right. Can you see the terminal window here?
Yes.
All right. So I'm on that, just to go back to this topology view, I'm on this ADB target. This is where this terminal is. And we have a little wrapper for ADB. We can show all the devices that we can reach. So if you had more than one UE associated with your experiment, they would all show up here. I can connect to all of them using the PhantomNet ADB -A command.
Kobus,
so now,
one moment. I just wanted to let people know, if you click on the 1:1 button that shows up when you put your mouse down near the bottom of the screen, you'll actually be able to zoom in and see the text more easily. So if you're having a hard time seeing the text, go ahead and click on the 1:1, the 1:1 button, and it'll allow you to zoom in and kind of move around the screen in a zoomed in way.
Great, thank you. So let me just go to the MME console again. So now we can do for those of you who are familiar with Android ADB commands, we can do all these ADB commands like you would do with a normal phone connected to, let's say, your laptop. Right? So I can do a shell on the device. I'm on that physical phone now. So I should be able to ping this address. And you should have seen this activity in the background. So a couple of things to point out here. this phone has been idle for a long time, right? Even though the experiment was swapped in, it was idle. When your phone goes idle, all of this state that we talked about before in the network gets cleaned up. And so when I did the ping command, the device obviously had something to send. And so the tunnels, the state had to be reestablished. And this was all this activity that we saw in the background here was related to that, to reestablish these GTP tunnels so that we can go out all the way to the internet. Now, as I was talking, you might have noticed that we got this context release complete, right? Since we only send a couple of packets, and then the device went idle again, and again that the state got released. Right. So if we do a ping again, lots of activity, the error gets established again, and you know if I stop it after a while, it would again be torn down. Right. So sort of, and again, I don't know how familiar you are with mobile networking, but this is, of course, fantastic technology, but all the signaling is also significant overhead. And if you have, for example, a IoT device that wakes up and sends 1 byte of data, then this is huge overhead involved in setting up connectivity. All right, so one more thing to show. If you So there's also tools that you can use to sort of remotely access the device via Adb. This is not, how shall I put it? This is not very user-friendly. It takes a little bit of time to get used to. There's a fairly long lag between interactions, but at least it allows you to interact with the device. So one of the tools we've been playing with is called Calibra. So you can connect to that like you would when you use Calibra on your own environment. And this then basically comes up with a little X window that shows you the device. Of course, the device is asleep, so we need to wake it up first. So I can remember the right command here. Oops, no, not that one. Refresh. No, I think it should have been wake up. Oh, there you go. Right, so this is our Android device. So we can start up applications. Again, in the background, you'll see we started up the browser. The browser contacted something on the internet, and connectivity got established to enable that. It seems to be taking its time to load.
Kobus, this is Kirk. If you hit F5, it should refresh the display.
All right. Oh, there are problems with security certificate for the site. So this is a problem we ran into recently where the device, the phone gets its time from the network, and it looks like there's a bug in the OpenETC software stack that sets the time incorrectly. Basically, it looks like a null time field, and so it gets set to the beginning of Unix time. And then when the browser tries to do its certificate, it complains about this discrepancy. So I'm not going to try to fix it on the fly here, but I mean, basically, you can tell from this how you could interact with the device using Calibra. Okay, I think that's pretty much it. So let me go to my final set of slides, and hopefully you can see this now because I'm sharing the whole screen. So what does this all mean for you? Well, we think we have a fairly useful set of functionality. We're looking for users. That means you. If you have any research or teaching, we would love to support people doing teaching as well that you think would fit PhantomNet. Please contact us. The process is pretty much you would come in, you would create your own project. If you're a student, you would need to get your advisor or someone senior to create a project. And then once you have a project, you create your own experiments and you manage your own access, for example, for your students, if you're a PI or faculty member. That's pretty much it. Any other questions?
Any questions for Kobus? I believe we had people from as far away as the United Kingdom joining us. So we're glad for everyone that has been able to participate. One more call for questions, and then we'll finish up. All right. Well, thank you, Kobus, again for your time and your talents in presenting this to us and for making PhantomNet a reality. I just wanted to remind everyone that the next GENI webinar will be on July 15th, which is just 3 weeks away. And Mike Zink is going to be presenting to us, and so we'll look forward to that. And that's going to be at a different time. It's going to be 11 a.m. Eastern time. So we'll send out some emails and let everybody know more about that.